All right. Hi, everybody. We're going to wait a few minutes for attendees to start trickling in. I see already a few dozens of you are being admitted. Look at that, 30. Numbers go up. So in about 1 minute, I'll kick us off. Very exciting to once again be holding one of these Coredump webinars. I always have a lot of fun doing these. We get amazing questions from the audience. It's honestly one of the highlights of my job here at Memfault. Okay, I think we're in pretty good shape. We'll get started. So welcome to yet another edition of the Memfault Coredump webinar. As always, my name is François Baldassari. I'm the founder and CEO at Memfault. I'm also an embedded engineer who's worked on a number of devices across consumer and enterprise IoT. Joining me, as always, is my co-founder, friend, and Memfault CTO, Chris Coleman, who I've worked with most of my career and is the brain behind most of the technology we build at Memfault. And this month, we have joining us Alexander Samuelsson, who's the CTO and co-founder at Imagimob. Alex has extensive experience building and delivering edge AI applications. He started an edge AI company in 2013, long before it was cool. He's currently leading the development of Imagimob's edge AI platform, DeepCraft Studio, within Infineon. It enables customers to quickly build and deploy their own AI applications for the edge. Alex, welcome. Glad to have you here.
Thank you, Francois. Thank you, Chris. Thanks for having me.
The topic today is the future of edge AI and what it means for device makers. And if I kind of peel off the marketing speak a little bit, really what we want to talk about is, should we care about this edge AI stuff? What is it really? And how might we start getting used to it? Or how might we start learning and applying those techniques to our own projects? And we're so lucky to have, of course, an expert among us. As always, if you are on this webinar live, you can ask us questions. You will see at the bottom of the Zoom UI, there is a Q&A button that you can click. When you enter a Q&A, we will see it appear and we will either write you a response directly. We might answer it in line because it's very relevant to what we're talking about, or we will have a Q&A section at the end and we might cover it then. And with that, we're going to just dive right in. Alex, tell me about edge AI. What is edge AI? What kind of AI are we doing in embedded? Give us the 30-second elevator pitch for edge AI.
So I'm glad you mentioned embedded because there's this confusion about edge AI. What is it? Is it in the edge of the network? Is it in the cloud? But we at Imagimob, we are talking about edge AI on embedded devices.
On the real edge.
On the real edge. And there it really adds a lot of value. I mean, by processing data as it comes in on the edge device, you only need to share predictions or actually only share the actual value extracted, and you don't expose that personal data. And running that close to where the data is captured, you can also do applications that you can't do in the cloud. So, for example, you could be sitting with your application in a robot somewhere, and you recognize that there's a person coming close to it, and you stop it right away without relying on a connection. So
with zero latency, yeah.
Zero latency, full privacy, and some applications that you can't even do where the AI is located in other places, I think is a pretty good value proposition.
So maybe in summary, edge AI is in the context of this conversation, especially AI models deployed on embedded devices that are in the world. There's a number of reasons why we might want to do that: privacy, latency, maybe others. We'll talk about that more. But I think importantly, edge AI is quite different from what people have in their head in 2025 when they think about AI. Chris, are we talking about LLMs at the edge, or what kind of models are we talking about? I'll be also curious to talk about, real world use cases.
Yeah, I mean, when I think about and yeah, I guess let me know if I'm wrong, Alex, but when I think about sort of things operating at the edge, I think of much more finely tuned sort of recognition algorithms for certain patterns, whether it's, fall detection or sleep detection or sort of very particular types of image recognition. And so not as if we're mapping down to an embedded device, we're facing, constraints. And so we have to kind of tune things to just focus on sort of specific areas. I feel like the most common one I think of is just image recognition related things running on cameras and items like that.
Yeah, so I would agree to that. It's more fine-tuned. You have to get everything, all of the power out of the device. So it has to be more fine-tuned. But things are evolving really quickly. But I would say you're kind of looking at where AI in the cloud were maybe 10 years ago. And now we'll get to that later, I think, with the hardware advancements that are being made, that gap is shrinking. But yeah, looking at the typical use cases today, it's, fall detection or sound recognition, simple voice interfaces, object detection using cameras, kind of niched applications. But the possibilities are growing and growing.
And these are all possible. Like we're talking about these applications, object detection, natural language processing in some ways, right? Language understanding, time series data analysis, and very quick kind of sensor data processing. We're talking about deploying those on microcontrollers, right? Like I think it's important. Oftentimes when I talk to device makers, they will say, well, I don't have the power budgets, I don't have the cost, I don't have the dollar budgets, the budget to put an NVIDIA Jetson in my device, right? It's too big, it's too power hungry. But actually, I think now a good number of companies are deploying edge AI models. In fact, I actually like to use the word ML models for these specific use cases because they're very different from what people envision when they think AI. But these ML models, deploying them on microcontrollers, I have, I've seen Infineon, for example, has a number of chips and SDK updates to make it very easy to train and deploy these AI models. The PSOC 6 AI, I know, was one of the big announcements last Embedded Worlds. There you go. You've got it representing. And so we're talking about very small power envelopes, very low cost devices that might in the past have been just your Bluetooth MCU, right? Is there kind of some subtlety to what kind of devices can run these ML models or not? Or is this more, you tune your model to your specific device?
Yeah, so yeah, of course, you tune your model to your specific device. And that's something that it's an important part of the tooling and our DeepCraft Studio platform, the ability to do that. And then, of course, you have to consider a little bit where you're deploying in terms of what use cases can you run there. But if we're talking about like even the most simple ARM Cortex M4 platform, you can still do quite a lot. I mean, you can still do like simple voice interface. You can still do even really simple image recognition. So, and you can do pretty advanced like signal analysis on this envelope. Then if we go with more powerful microcontrollers, then we can do like more advanced vision applications and
and by the way, like many Cortex M4 have SIMD instructions and DSP extensions that can be used to accelerate ML workloads already. So I think we're only going to see more of that. I'm sure that every semiconductor is going to roll out their own proprietary AI, processing unit or NPU with some neurons of some sort. and that eventually some standard will emerge, and or ARM will come up with really compelling silicon, and we'll all be using that soon enough.
I hope so. We're really looking for that standard, and that's some of the value that our platform and other platforms are trying to fill. Today is really difficult to deploy on some of these devices with NPUs because depending on what device you're deploying on, you have to change your model or you have to do a lot of hand optimizations. And we're trying to kind of remove that struggle from the machine learning developers and the embedded engineers to just like focus on the application, focus on the data, focus on the model, and then see what's the best model that can fit on my device and making sure that it's really performant when it's running there.
What are your thoughts of some of the
Chris.
accelerators? So if I think about, I think about where we started Cortex M4s like a decade ago. We have like M55, we have U55 stuff starting to come out. Like what's been your experience of working with some of those accelerators today in terms of like use cases they unlock or developing with them?
So, I mean, first of all, this is like the embedded industries, I would say like GPU moment. If you look at machine learning, when we figured out like more than a decade ago that we can run these models on GPUs and unlock this massive performance, that's now happening on embedded devices with the NPUs. So, I mean, it was amazing, almost like shocking, because overnight, going from an M4 to a M55 plus U55 we're talking like 250 times compute performance. And then more memory as well. Memory is still catching up. We don't have 250 times memory yet, but
it's an interesting constraint problem. So there's so much more you can process, but probably keeping the buffer size on the memory in the right place is really tricky.
Yeah, but that just means that like overnight, we unlocked all these things like really high performant object detection, putting like analyzing high resolution camera images in real time, tracking multiple objects of different kinds. And now, we're even looking at image segmentation, which was unthinkable to run on a microcontroller, unlocking use cases like in robotics, even like having a lawnmower, like a robotic lawnmower or robotic vacuum cleaner, understand which objects do I need to avoid, what surfaces can I go on, and so yeah, 250 times performance. What is that in Moore's law? I mean, it's like almost a decade of progress.
Yeah, super cool.
I think one thing that is clear to me is that these ML systems are just so well matched to the embedded use cases. And I'll explain what I mean. Like in embedded, oftentimes we're limited in compute, we're limited in memory to some extent, we're limited in bandwidth. And so having the ability to do a lot of the work offline, upfront, in the cloud to train the model, right? Because in effect, build these ML systems, the compute is split into two phases. You have the training compute, which can be huge, right? I mean, to train some of the big AI models, they're doing GPU months or GPU years of compute. But then you get a model that you only need to run a little bit, fractionally speaking, a tiny bit of compute, relatively speaking, to do the inference and to get an output from this model. And for me, this feels so well suited to embedded, where you can do all this work up front and then do just a little bit more work and get some new capability on the device. And so this is, for me, the crux of AI on embedded, and why a good sign that it is not hype, because it's just so well suited to the subject matter. And so, and in fact, Chris, I was going to turn this over to you. We are seeing our customers use AI at the edge. Like the other proof that it isn't hype is actually people are doing it. People have been doing it for a while now. I know, Chris, at Pebble, I remember when we were building some of the voice commands, we were trying to do voice commands on the watch, and we had investigated a tiny little neural net in 2015 that could run on the Cortex M4 and detect like 8 different words. That was already a really exciting use case, and using ML methods. Is there any other customer or real world use case that stands out that you've been very impressed with, Chris?
Yeah, I think a couple standouts. So, I think what we were talking about early on, some of these, we want to trigger the device to wake up, or we want to prompt something, and we want low latency. We don't want to send things. So like simple voice keyword recognition is something that comes up. I think everyone in the camera space these days, in terms of like recognition, object detection, sort of fancier things there. A lot is coming up. In the wearable space, yeah, better sort of like activity tracking, what phases are people going through, like mapping that down to the device. I think those are kind of the ones that stand out to me.
A lot of the new systems you see, like the Apple Watch, the iPhone, ship a lot of new type of analysis, right? I'm not talking about the LLM powered, like, asking it questions, but rather things like blood sugar or blood oxygen level. All of that are actually powered oftentimes, I don't know about the specific implementation for Apple, by tiny ML models that can do things that traditional algorithms can do.
Yeah.
Alex, do you have an applications, like a customer story, something that for you just blew your mind, you think was really excellent?
Well, I mean, one of the really cool things I think is you talked about the Apple Watch. I think what they're doing with the electrocardiogram analysis,
Yeah.
and actually figuring out like if you are having anomalies and telling you to go and seek help. So I think there's a lot of health applications that are really interesting. We were doing fall detection really early for the elderly. I thought that was really cool because we could do it with Edge AI, also with a tiny network on a battery-powered watch with the non-rechargeable battery for the elderly that would last for months. One that was really cool and recent was within the manufacturing industry for automotive. We worked together with a company, and they had welding experts, which could listen to the welding robots and understand the quality of the weld.
Wow.
So then we tried together with them to collect this audio data and mount a little embedded system with a microphone on the welding robots. And it was amazing the like minute errors that it could pick up. So things like, I had it explained to me by this welding expert, like if you put the wrong thread in, welding thread, it could differ by like sub-millimeter width. The model would pick it up and tell you like, okay, you need to stop, you need to fix this issue.
Moving on to, actually implementing Edge AI in your products. Like, I guess let's start with, let's say you're an embedded engineer, and you've been tasked with building by your marketing and your CEO to build an AI device, an Edge AI device, and you have to figure out what you're going to be able to do. Let's first start with hardware selection, right? What and any critical requirements that we'd want to take into account? Like what do I need to make sure as an embedded engineer who's going to have to actually deploy these models eventually in my software? What do I need to make sure I tell my electrical team to include? And how might I also future-proof my design? Alex, if you want to start us with that. And you're allowed to say PSOC 6.
Yeah,
But
exactly.
hopefully we go broader than
PSOC
that.
6 AI kit has a lot of good sensors on it. No, but one thing that I would really pay attention to is the sensors that you need for whatever use case you're building. I mean, let's say it has to do with motion, really, do your research on the accelerometer or the IMU to make sure that it can be always on within your power budget, that it has the resolution that you think you might need, and you should play around and test that a little bit, look at the data. Then of course it's always good to leave a bit of extra memory space, because we've been seeing this so many times early on when we were in projects. We had an allocated like memory budget for the machine learning model, and then it's always something else eating into that budget. So that's good to have some margin there.
I feel like it's also a situation where like once you have one thing working, then the product and marketing team are like, why don't we add two things now? Because this is so valuable. And then before you know it, that budget you modeled for, you're really pushing the limits of the RAM and the flash that are available.
Yeah, I completely agree with that.
There's some guidelines, like for example, Imagimob. If I want to use Imagimob to deploy an ML to my device, do you have guidelines you give in terms of, for example, code size, RAM? Like, I assume you have a runtime, right? I don't know what you use under the hood, if it's TinyML or something else, but I assume you have a runtime that takes a certain amount of space. And then the models, each model is different. But I imagine you have some rules of thumb. So maybe you can share with us, like, what are we talking about in terms of code size and RAM to build, your classic, let's call it, IMU, like time series data analysis algorithm?
Yeah, so really good question. So on the runtime, we have a lot of different backends, so that varies. But if we look at the use case level, yeah, working with IMU data, I would say you can get pretty far with just like 10Ks of RAM and 20K of flash. If we start bringing in sound data to do like detect different sounds or simple voice interfaces, then it's more like 100K of RAM, maybe 200K of flash. And then if we go into like really state-of-the-art object detection with the camera, then it's more like around a megabyte.
Or just a frame buffer will run you that if you're talking about a color image, right?
Exactly. So then it's like 1.5 megabytes of RAM, maybe 2 megabytes of flash, minimum, absolute minimum.
Got it. Chris, any other recommendation you'd give if someone is trying to spec out their hardware for to deploy Edge AI? What would you be careful about?
I mean, I think it kind of traces back to either upfront, do your research and really know what applications you want to target. Because I feel like based on the complexity that you're going after, the problem you're trying to solve really kind of gives you a shape of, what footprint microcontroller do I need to select? If your business model can afford it, I don't know, if someone's buying a subscription for the service or like what's in place, like don't cheap out, spend the extra 50 cents so you have the RAM and flash for like future expansions and where things go. And then, I mean, the other thing I think about when we're talking about models and sort of like wanting to test things is you're going to want to have enough flash space to do things like update the device, maybe have like a couple, like you need more than your base image so that you can A/B test this stuff in the field, look at performance, run a couple different models and see what's taking place. So those are I think those are some of the areas I would think about.
Do you two think it's practical to run these models on battery powered devices? Because we've talked about, memory and flash, all of the actual hardware resources, but of course the inference will cost us some battery. Are these being deployed? Are these models being deployed in battery powered systems, or is that still a challenge?
Also definitely. And not only simple use cases. So, I mean, I told you about the watch example with fall detection with like 6 months of battery life. But if you look at these, more recent architectures, for example, Infineon is releasing PSOC Edge, which comes with M55 and U55, which is the hardware accelerator for ML models. but it has a low power and a high power domain. So paired with that, it has a tiny machine learning neural network accelerator and an M33 core. So you can do like first stage of analysis always on, battery powered, and then you see something that might be interesting, and then you wake up the bigger core and have a bigger model. So this is becoming more and more common, that you have like a part that is always on.
I think that's the strategy I typically see, is like you either have some very simple thing that's running always on where you can boot up and do something more sophisticated, or it's even dumber than that, and it's like, a wake up interrupt on an accelerometer when there's motion kind of triggers the system to run a deeper analysis, and the full kind of microcontroller itself is in a stop or a sleep mode when activity or things aren't taking place.
Yeah, so in effect, this is a little a natural extension of the low power islands architecture that we've used for sensor fusion in the past, where, for example, working on virtual reality headsets, you'd have a little MCU that could do sensor integration and monitor for interesting events, and then would wake up the big CPU that ran Androids only when you really needed to.
And if you're talking about like the M55, that's like 250 times faster at like analyzing something than an M4 was in the past, yes, that means you can run much more sophisticated algorithms, but there's also it's much more efficient from sort of a power to compute ratio. So you can spin the thing up, be done 250 times faster, and then be back into a low power mode and kind of push out, the life you're getting on that battery enabled device.
Yeah.
Let's talk about the actual firmware, the frameworks being used, and we'll eventually talk about training the models themselves. But let's talk about inference right now.
Mm-hmm.
What does the firmware look like? As a firmware engineer, what's different? I think I'm curious to hear from you, Alex. Also, is TinyML the main the big game in town, or are there actually multiple frameworks for running these ML models at the edge? What should people be looking at?
Yeah. So with TinyML, I guess you're referring to TensorFlow Lite Micro, right?
Yes.
The inference engine. Yeah. We are using, so we have different inference engines. We have our own proprietary one. We're also have a backend with TF Lite Micro. If you're using DeepCraft Studio, we're making sure that the API is consistent, so you don't have to care about all of those details.
Got it.
And you can bring your own model into that and leverage that.
So the engine is like it's a checkbox basically, which inference engine is being used, and there's not really any coding required.
Yeah, basically like that. So the interface, like the API, is just since we're an end-to-end solution all the way from collecting the data and training the model and optimizing and deploying it, we keep track of how the data looks like coming into your model. So then when we generate that API for you, it's like you have a function for ingesting sensor data or whatever modality you're bringing into the model, and then a function for getting outputs, predictions of the model. And then, of course, a function to initialize it all, clean up the memory and so forth.
Where do people get hung up more often than not? Like what ends up being difficult for them? What are the obstacles?
So I would say, like everything machine learning, data is a big pain. So how do I get high quality data? And when it comes to edge AI and embedded devices, it's like first I need to collect high quality data, but then I also need to collect data, on top of that from my device, typically as real as possible. Because let's say it's audio and you have some packaging around your device, you want to really have that as part of the training and test with that. Or if it's like a device that you wear on your wrist or something like that, then it's, you need to actually go out and collect data, which can be
Is there like a
painful.
recommendation on how much data someone needs to collect to kind of get to the accuracy that's there? I think about your like welding use case, right? Or sort of examples like that where someone's training a model. How much data do they need to record and collect to kind of get things to where, where it's sort of accurate and working?
Yeah, so the boring answer is like it depends. But to try to give people a guideline, you know, you need a few thousand samples, minimum to make a good application typically. And by that I mean those could be short. So when it comes to this welding use case, it was not like we collected days or months of data, but hours of data in different scenarios.
So will people typically write a first firmware that's just a data acquisition firmware? Like let's say I have my dev boards or maybe even my form factor prototype, because for example, for audio, the audio performance might change with form factor and dev boards. So let's say I have my prototype is the thing to do to first, before you start working on your product feature development, you'll build a little data acquisition firmware, which just plugs into a serial port on your laptop and can stream data for your sensors. That's the recommendation?
Yeah, that's a really good way to start. Yeah. Yeah, for example, we have a protocol for that. Others have that as well. But you can add that to your firmware, and then
also you have a library. You can drop a library and for data acquisition that's going to get data in the right format.
Exactly, and then it will work with our platform. You can collect it directly in there and visualize it and listen to it. But you're right, like you need to be able to collect data from your device. You can start without it, to prove your use case. You could collect, say you're doing keyword spotting using a microphone. Of course, you can start just collecting that on your PC or pull down a data set and see if you can make a model that performs well and is small enough. But then you should really take the step that you are talking about to make sure how well does this work on my device with my microphone in my casing, or yeah.
And for getting the data off the device with your library, is it sort of do folks usually sort of stream that over serially, or do they kind of like post it up over Wi-Fi or Bluetooth or something like that? How does that usually work?
Yeah, so currently you can do it serially. We're adding like Ethernet support. So now people do that on their own.
I remember back when we were working at Pebble trying to collect raw data for certain areas. It would be like, you could analyze it on the device, but you tried to push it out over a slow UART or something like that. You'd overflow the buffers that were there, and it actually turns into a interesting challenge. Can I write the raw data somewhere fast enough where I can then go and look at it?
I mean, for video data, that seems like a real challenge.
Yeah, I mean, I would say camera is typically a bit simpler than a microphone in the sense that the sensor is more kind of standard. Like an image is an image.
It might be like USB enabled, or it might have a USB interface already and be, you can plug it into a UVC, USB via UVC, and get images on your laptop.
What we see with some of our customers is that sort of, form factor, sort of initial prototypes will have a slot for an SD card and just kind of like write as much data as possible coming off of the device onto the SD card for internal analysis or kind of data collection. And then sort of like those can be offloaded and uploaded. And I don't know, honestly, it seems like a pretty good strategy for have a way to save off the raw data wherever you are. And then you can at least like use that for deeper analysis.
Yeah, that's a pretty good approach. I mean, then you don't have to figure out the connection and the bandwidth. And
how do people do the labeling? So it seems to me, when I think about building an AI system, it feels to me like the labeling ends up being the hardest part of the whole thing, right? I can understand how I will take my device and collect a bunch of sound samples, let's say, using your welding example. I can understand that. I can understand how I take my samples, my labeled samples, and I plug them into the Imagimob black box or whatever training system black box you use, and it spits out a model. And I can understand how to use some inference engine to run the models and get an output. But for me, the step of getting like thousands of samples that are labeled properly so that because you need the inputs and the desired outputs to train your model. Is that the most expensive part? Is that where people put most of their energy?
It's
And
certainly
do they depend on third-party services? Like what do most of your customers end up doing? Is that something you help with?
both, I would say. I mean, we help with recommendations and yeah, and we have partners where we have partners doing labeling for us, and customers do that also on their own with partners. And of course, yeah, I would say maybe this is not the most time-consuming part, but yeah, if you would do it manually, it's certainly the most boring and tedious part. But here we can leverage all these advancements in the cloud. So you can use this multimodal, more and more people are doing this. You use these multimodal LLMs that can understand images, for example.
Yeah.
And then you have them like,
do the labeling.
Yeah, label this for me.
So love that. And I actually think that this is a technique that's becoming more and more common, both in edge AI and in standard, cloud AI, which is use a very, very capable model, a very powerful model to do some of the labeling and or generate some data for you, even some data generation for you, to then train your tiny model. It's in effect, it's a form of model distillation. That's, I think, a reasonable definition for what distillation is. Super interesting. What do you think when you think about edge AI as it exists today and as it will be in the next few months, let's say? Are there specific use cases or verticals that you think are going to be very highly impacted by AI? Maybe Chris, starting with you. Specific verticals or use cases that might not already be AI dominated, but you think are going to be, places where we all use AI routinely at the edge?
I think one of the areas we talked about at the beginning of the session in the health space, sort of like upfront analysis that you can do from super, super low signals or kind of things where we couldn't extract insights before. I think that's a space that's going to be impacted. Like what applications when it comes to health analysis can we bring to people via wearables or two things in their house? So that's one that really comes to mind for me.
Alex, what might be maybe turning the question around? What might be one where it's not going to be the case? Like what are going to be some impediment to adoption and verticals where we're not going to see AI for a little bit of time?
Oh, so I think so. It's definitely happening, and it will happen in a more faster pace in consumer electronics.
Yeah,
because there's not a lot of like demands or security requirements depending on the application. So yeah, turning it around, like those areas where there's a lot of regulation and demands, things are slower.
yeah, because one of the challenges is that these models are very hard to characterize, right? Like I hesitate to say they're non-deterministic because the world is deterministic, right? But for all intents and purposes, they're non-deterministic. You can't really guarantee through inspection that a given input will give you a given output. That kind of defeats the point of ML if you could, right? If they were so algorithmic. And so I imagine that anything safety critical, anything, certified in some ways, right? Like I don't think UL or IEC has developed guidelines on how to get your AI model IEC certified or UL certified. Anything that's going to go into space or going to an airliner or a car, right? I imagine it's going to be a little while before, in critical places, the models are deployed routinely, and that's probably a good thing. I mean,
yeah.
Yeah, I mean, ultimately, many of those industries you mentioned run just like 10 to 15 years behind whatever's happening in consumer electronics or kind of other industries, maybe with less regulation. So like AI applications in space or AI applications for, fire detection or whatever it might be, and sort of something that is highly regulated there, it's probably going to show up in like 2035.
Yeah, you're right. Like it's like everything going into those industries. However, I mean, I'm not an expert on this, but I've heard several use cases for edge AI in space. So I think that's something that's already happening
Yeah,
because of like the
actually,
low power budget and like analyzing pictures and satellites and.
this is a little bit of an aside, but space is one of those, as an engineer, I always expected it to be super highly regulated. But actually building, you know, if you're SpaceX or your Planet, you're building low Earth orbit satellites that are commodity, it's very unregulated. The software is not certified. You can build whatever software you want on there. It's quite surprising. And so, in fact, if you tear apart some of these small low-cost sats, they're practically consumer electronics in their
amazing.
design and their software. I found that really, really interesting. Of course, there are those that serve defense use cases. That's a whole other ballgame. Yeah. But I'm not surprised we're seeing models in space, because I find that aerospace is not space, right? Like airliners, super regulated, but small sats, I'm sure they're very cutting edge. Do you think so? One of the things we haven't talked about much yet is that AI at the edge, you know, AI in the context of building edge products isn't just about running AI at the edge. It can also be the pairing of AI and cloud AI and device. Are there, you know, how do you think about the separation of workloads between an edge AI model and a cloud AI model? You know, I think there's some obvious answers there, but I bet you've thought about the topic more deeply than others, Alex.
Yeah, so just like we were talking about how on the embedded device you have different power domains, I mean, that stretches all the way up to the cloud. So that's
exactly the cloud in a way is a power domain.
Exactly. So you can do your analysis on the device, but then you can, you know, take that buffer that you use to make that decision and send it up to the cloud and get, you know, even more advanced analysis, or get into a mode where you stream a bunch of data to do something really advanced. So yeah, I think you can kind of stretch that domain all the way to the cloud.
Yeah, the best applications are going to be hybrids in the end, right? And on the edge side, you have the benefit of very low latency. I think it's going to be very hard to have a cloud AI model run and give you an answer fast enough that it can do something like, you know, stop a saw that's about to cut a finger. So latency is a big advantage. Privacy, as you mentioned early on, big advantage. There are many users who don't want raw audio streamed to the cloud or raw video streamed to the clouds, and having an AI model that extracts features, doesn't even need to do the whole AI pipeline, but just extracting features for an image to make it more privacy respecting feels like a very good use case for AI at the very edge. And then last but not least, go ahead, Chris.
I said, and bandwidth. Like we work with a ton of customers who are, you know, asset tracking, cellular, satellite-based applications, and they just don't have the bandwidth to send things up all the time to a cloud that fits within, you know, the data budget that they can send, or just the transport that's being used, right? If you're using LoRa or something like that, you can send hundreds of bytes a minute. So like I think
AI is amazing at domain-specific compression, right?
Yeah.
Like in effect,
yes, that's a good way to look at
like
it.
extracting features from a very data-rich system is a form of compression, and AI is really, really good at that. And so you can in effect think of it as like pre-extracting features as a form of compression. We can save a ton of bandwidth.
If you could turn a ton of accelerometer data into, you know, a Boolean fall detected.
Yeah, exactly. That's a pretty good compression.
Amazing compression ratio.
Yeah, I think the last thing we don't talk about enough when we talk about edge AI is costs. I think it's very cheap to run a little model at the edge. Once you have the cloud in the loop and you have a big complex model in the clouds, you very quickly start spending dollars per device per month on inference, right? Yeah. If you're trying to pipe a bunch of device data to OpenAI, your bill is going to be a big surprise. And I think that
Yeah.
that's a constraints that people are starting to wrestle with and don't have a good handle on. Right?
Yeah, and predictability, right? Like of that cost, you're becoming, you're kind of in the hands of that service provider that might increase those costs over time, over the lifetime of your product.
Turning to the future, I'll start with a question on business models, or how do you think businesses are going to change with AI becoming more and more prevalent? Like what's your prediction as like the business impact for the device manufacturers?
So this might not always be the case, but I think we will move like more and more into this kind of service-based economy or business model, because okay, we've been able to do over-the-air updates to devices for a long time, but with models and with having a model on a device doing something, being able to improve it over time, because you might also extract some data from the your fleet of devices. I think that has value to customers to say like, okay, you're buying this thing, and if you keep paying, it will actually become better and better over time. And we might add, with these more capable devices with more memory and more compute, we'll be able to add another model to enable another use case. So really the longevity of these devices, I think, will increase. And that kind of speaks for this business model where you can, you pay for some of this value being added over time, or at least you have the possibility as a customer to do that.
I completely agree that it's going to accelerate the transition to hardware companies being more software company-like, because these AI models present a tremendous opportunity for iteration. In fact, they require iteration, right? You're going to ship the first version, you're going to get real-world data, because the system is non-deterministic. You're going to find that there's ways in which it doesn't perform how you expected it, and you're going to want to gather more training data and continue updating the models, and that upkeep costs money, right? And so you're going to need an ongoing revenue stream from your hardware fleets in order to support ongoing developments, but also the value you're going to deliver hopefully will be very high on an ongoing basis. And so hopefully will justify that additional subscription. I also think, I'm obviously drinking my own Kool-Aid here, but I imagine that observability is going to become more and more important.
Yeah.
Because we don't know what those AI models will do, we can't just QA the hell out of them and then hope for the best, right? We have to measure how they actually behave in the field, and we're going to need some sort of observability to make sure we can create this feedback loop and observe that the AI models are behaving the way we expected them to and saw them behave in the lab, right? Anything you'd add, Chris?
Yeah, no, I think that's a great point. And I agree. Yeah, I agree with what both of you said. I think when it comes to the models, having an area people are still getting in place from an OTA perspective, but being able to sort of update and try different models and sort of measure what you're seeing, understand what's improving, understand where things are possibly going wrong. Your device can now get into more states. So I see that as an area where I imagine more and more questions will pop up.
We're at the 50-minute mark, so I'm going to turn it over to some questions. We've got a bunch, so I'm going to start with some Imagimob questions. We have one that I'm sure you hear all the time. Are Imagimob tools tightly coupled to Infineon parts? Abderazak is asking basically, can I use Imagimob with non-Infineon parts? I assume he or she already has a design and would like to use Imagimob. They're also asking about how the pricing works, if that's something you feel comfortable talking about.
Yeah, sure. So it works with non-Infineon MCUs. So you can use it for pretty much any MCU. There's even like you can generate C code like without any dependencies and run it pretty much everywhere. since we're an Infineon Technologies company, like we're really leveraging the kind of user experience that that is a bit improved on Infineon hardware, but you can use it with anything. And also, well, we have different offerings. You can buy like off-the-shelf models that are already pre-trained and works brilliantly for their use case. Then you pay royalty per device, regardless of what MCU you're deploying it on. Or if you use DeepCraft Studio to build your custom models, then development is free, regardless of MCU. But once you're deploying a custom model, it's also free on Infineon MCUs, but there's a royalty fee per device on non-Infineon MCUs.
Got it. Makes sense. We had one other user asking about DeepCraft Studio and curious basically on what kind of finding it complex. I think these systems are still relatively complex. And so they're asking like what, streamlining or new improvements you have in mind to make it as easy as possible for someone who's not an AI expert to get up and running. Maybe you have some things to share. I assume that that's a complex question.
Yeah. I mean, okay, something that I think is like really interesting for people to know coming up is we're adding end-to-end. We talked quite a bit about object detection using cameras. We're adding a really nice end-to-end workflow for that. So that's a big step in terms of usability for that use case. But also in general, we're working a lot on improving the user experience. We've done a lot on collecting data more easily from your devices. And also we're doing a lot of improvements when it comes to processing that data on the device. So it's becoming easier and easier every day. And, the
world never stops.
The world never stops. But yeah, we're working really hard on the user experience, really simplifying those user journeys.
Roe asked about, I think, a question that's really important here, which is, can we trust embedded AI models to be consistent? I would edit the question and say consistent enough, right? Because I think with any application, there's a tolerance, right? We have to define tolerance, but can we trust them to be consistent enough if we train them with very high quality data? And Roe gave us the context that they're considering using ML in a product for significant movement detection and identification, but isn't sure whether it can be reliable enough. And so he wonders, or he or she wonders, whether that's ready for commercial and production use cases, or if this is still in the realm of proof of concept, and how we might convince ourselves that it's production ready. And I'm sure you talk about that all the time.
Yeah. No, so I mean, you can always reach out to us. We can look at your use case and give you recommendations from the vast experience we have from different use cases and projects. So I mean, you have a lot of use cases that are proved to be like production quality, production ready. We talked about object detection, where there's super high accuracy. It's used in real products. Same for voice interfaces. And when it comes to custom models that you build yourself, this is always the challenge, right? Like, before you start developing, how certain can you be that you will get the performance that you need? But we can offer a lot of guidance there through our experience.
Yeah, I think off-the-shelf models are oftentimes reasonably characterized. Not perfect, but reasonably characterized. And so if you read the accompanying paper and the data sheet for the model, you oftentimes should have a rough idea of how it will perform, what the range of performance might look like. And I think that can be, there may be some life and death use cases where still you may not be comfortable with it, but I would say for the overwhelming majority of use cases, they will work well. And certainly is beyond proof of concept, because we are seeing companies deploy this model commercially and get really, really great results from them. And I think if you want to get some intuition for that, I would say that if you look at model, AI that ChatGPT, some of these systems like that, the hallucination problem has actually improved significantly. And nowadays, a lot of people trust these systems already as they do Google, right? Whether they should or not is a different story, but we can see that we are learning how to make AI systems more reliable. And so ultimately, I think it's about making sure that number one, you understand the behavior of the model you're using, because we're oftentimes using off-the-shelf model. And then number two is you be careful between interactions between your data and the model. For example, time series models expect are really good at analyzing data with periodicity. And so you can't just give a time series model data that's chaotic and say, do anomaly detection. It won't work, right? And sometimes model makers don't do quite a good enough job of specifying the assumptions they make about the incoming data. I think that that's really something worth investing in more or investigating more. Anything you want to add?
Yeah, like you can always do a little bit of, there's a test you can do, a little bit of benchmarking. You collect some data and you divide it into parts and you see how your model performance kind of improves, and it will not be linear as you add more data, and then you get kind of a feel for, okay, how close am I? How much more data might I need? But I think a mistake that a lot of people do is that they're not testing on like a good real world sampling of the data. It's too much happy testing.
Right.
You're like, oh, now this is working really well. Yeah, because you're sitting and testing this in your environment and you're just iterating over that. So go outside, test in different environments, build small test groups.
We had two listeners ask about on-device training. So not inference, but actually running the training or fine-tuning of an ML model on device. Is that something you're seeing at all? It seems to me like it would kind of remove one of the main advantages of ML at the edge, because all of a sudden you're actually very compute heavy, but perhaps there are some cases where you've seen this happen.
Yeah. So it's a huge research topic, and there are some solutions that are used, like I think even in products for very niche use cases. So it works, you can do it. The trick is, like, how do you have a mechanism that is kind of proven that it will learn the right thing on device so that the model will always improve? So there you really, and that's where it becomes niche, because you really have to figure out that reward function or that feedback loop for the model. So it can be done. We're not really focusing on it at Imagimob because it's very niched. But there are companies that offers that. But I would say that the trick is you really have to figure out how to apply that to your use case. And it's kind of few use cases that can leverage that.
We've got a question from, we've got two questions around data collection and labeling, one from Jackson and one from Brent. Brent asks, what's some good metadata to collect when you're collecting your training data? He said, like, of course, timestamp, GPS coordinates seems obvious, but are there other things that people always forget to collect and they probably should? One thing in my mind is the firmware version they collected with, for example.
Okay, yeah, no, firmware version, that's perfect. Like one thing that we use a lot is video, if you can. So for an example, when we built these fall detection models and a bunch of other models, if you're looking at IMU data, you don't know if this is a fall or someone, banged their arm into a doorpost or whatever. But if you're there filming the data collection with the camera, you have kind of the ground truth. Same if you do gesture. We have models for doing like gesture recognition using radar sensors. If you look at the radar data, you'll have no idea what you're looking at. okay, you can do some processing and, you know, be more clear. But if you then have a camera stream next to that, you know exactly what gesture is happening.
So basically collect with your production system and also augment your data collection with a ground truth system that might be very cost ineffective, very bulky, very big and high data, but I will give you such good ground truth data that it's unambiguous in your training.
Yeah, and people to be aware of that, like that's one big thing, big use case for edge AI. That's like removing hardware if you have really expensive hardware. So for example, you can use a bunch of sensors to remove a fourth sensor, a fifth sensor, because they can estimate it. And then you, yeah, on your collecting the data, you have that sensor, and then the model does the job of that sensor, and then you remove it from your design.
And then I'll ask one last question and we have to break. And I apologize to those of you who asked questions who weren't answered, but Joao asks, is there maybe a universal quality metric for a model? Like, in other words, if I want to know if a model is well trained, are there some common techniques for evaluating the performance of the model? I imagine like what's really common but is obvious is that you collect data with ground truth and then you train on 2/3 of your data and then you retain 1/3 of your data for evaluating the performance of your model against data that wasn't trained against. I think that that's a common technique, and then you measure the error rates there. And of course, you'll have to know whether that error rate matches the error rate you expect or you can tolerate in your system. But anything else that people might use to know whether their model is at the performance bar? Is there some heuristics?
So, yeah, as you say, there's what you just mentioned that's really common, and there's like 1,000 metrics that people use that are kind of off-the-shelf metrics, which everyone use. My recommendation is to, you know, don't put, that's, you know, that will give you an indication. So use those things like F1 score, confusion matrix, to analyze your performance. But what's really important, and this is, I don't know, call it a heuristic if you like, look at your use case. What are you actually building? Like, think of it as a product. So let's say that I'm building a doorbell, and I'll identify myself with Face ID, and there will be a model running there. Well, what's important for your product? Like, how quick does it need to figure out it's you and open the door? At what distance? How often can it get it wrong? Note those things down and perform tests. Because I feel like a lot of people, they think about the model as a separate thing, but it's an integral piece of your product. So think of it as a whole system, like all these things connected. What's the user experience? Do you, like, you know?
So it's no difference to acceptance criteria for your product, right? Is it, hopefully you have decent acceptance criteria for your overall product.
Exactly.
On that note, great, thank you, amazing wisdom. We have to run, but we're very thankful to Alex for joining us today and sharing all of this about AI. Thank you to all of you who came and attended and asked us some wonderful questions. Alex, I'll give you the last word. Where might folks learn more about AI? If they need help from Imagimob, where should they look?
Go to imagimob.com.
Okay, easy enough. Go to imagimob.com. Thank you, everybody. Once again, we're Francois and Chris, and we're with Memfault, the observability platform for connected devices. And today was a conversation about Edge AI and what it is, how we can use it. We'll have more of these conversations, but until in the meantime, we hope you all have an amazing rest of your week. Bye, everybody.
Nice chatting, Alex.
Bye. Thank you, Francois. Thank you, Chris.